Now, the idea would be we're going to improve our events. Based on this unprovable sequence, I'm going to make a green. How about this one here? Based on this guy here, we're going to fix MLN. So when we go to MLN over here, we're going to add a guard. And the guard is going to be when n larger than 0. Add one guard. We fix the model. And then we'll try to, based on this one over here, we're going to add this guard here. And based on this one here, we're going to add an extra guard. D and less than D. So now, because we have fixed the model, what should we do now? If you recall the workflow. Once we have fixed the model over here, we should regenerate all the 4 sequences. All right, good. Let me just do a little bit copy and paste. So the way I'm going to do it is like this. Okay, if I may. Okay, let me do a little bit of, sorry, I should have prepared this before the lecture, but let's now do it quickly. Let me just copy this page. Okay. And we're going to regenerate. And first of all, the question is, how many do we have? 4, the same. So 2 from the guards, and also 2 from the invariant condition, the same. The only difference is we're now going to, oh, actually I have it here. I beg your pardon. I thought I didn't have it. Okay. So now the difference is, you can see now we got extra here. N larger than 0, N larger than 0 versus N less than D, and also N less than D. All right. I'll make some annotation for you. So this is the new guard for ML_in. And this is the new guard for ML_out. All right? I would suggest when we go back to the beginning here, this one here is already provable. Now we're just adding some extra hypothesis. It should be easy. You just drop it by monotonicity, which is okay. And for this one here, that was also provable before the fix. And by adding another extra guard over here, that's also fine. You can just drop it. It still be provable. Now let's now revisit these 2, which was not provable. Let's do these 2 together. Okay, these 2. So I'm going to do this one here and this one here. But for these 2, I would still suggest you do as exercise. And you can also check the solution on the slides. All right, let's now do these 2. Why are they provable now? So which one should we do first? Yeah, we can do this one first. Or even better, let's see where we got stuck. According to before, we're going to apply monotonicity first. And then monotonicity, we will be able to now use that new guard. Okay? And once we get to the new guard, we should be able to discharge it. Okay? Let's now take a look. Let me see some slides. And then we can come back here. All right, so this is something that's unprovable. So that's why we've got to strengthen the guard. And you will see this is another one that's also unprovable. So that's why we've got to also strengthen the guard. And then we fix the design. Right, so that's a new guard I just mentioned. Right, we got new ML out. Also, we got new ML in. Okay. And we got to regenerate all the sequence again. And we'll try to prove each one of them one by one. Okay, for this one here, this one used to be proved, so we don't need to worry. Okay, but it turns out we just drop more hypotheses to make it provable. All right, this one here, we still get the same P2. All right, this one is no trouble. And how about this one here? That one was not provable before. ML out invariant 2. Okay? So this one here is basically this one here. That was not provable. Let's try with this one first. So I try to stay a little bit closer to the slides. So when you study, you can see both. Now, how do we discharge that bottom left corner? Okay, we'll start with this. And notice that we do have the extra hypothesis over here, n less than d. All right, that's important. And first of all, we apply monotonicity to drop all the irrelevant one. And apparently, we should keep this one here for sure. That's really the point of adding that extra guard. And we get this. All right, n less than d, n plus 1 less than equal to d. Turns out, this just matches the increment rule. How? Let's go back. All right, let me just show you that. You just need more exercise, right? That's why I really want to spoon feed you a bit in the beginning. All right, so for this one here, we're going to apply monotonicity over here. And then we get n less than d, turnstile, n plus 1 less than or equal to d. And based on this, you can see n less than d correspond to n less than n here. N plus 1 less than or equal to d correspond to n plus 1 less than or equal to n. So that's why we can apply increment. All right? Pretty straightforward. And then we are going to do the next one. All right, let's see this one here. All right, this one here used to be not provable. So that was the MLN invariant 1, which is here. So I'm talking about this guy here. This guy here used to be not provable, right? You can see it was not provable before. So now with the guard over here, how should we prove it, right? Let's see some quick slide, and then I'll write it down. Monotonicity, again, what should we keep? Well, apparently, we want to keep this guy here, right? That's a new guard. Otherwise, what's the point? So we're going to keep the guard over here, and then we still got n minus 1. Now, what should we do? Which rule should we apply? It turns out it's just a P2 prime. All right? So that'll be the last one. So we're just going to drop everything. So sorry, not here. Monotonicity, for which we're going to get n larger than 0, turnstile, n minus 1 is a member of n. And this one, you can try to see it matches exactly that. I'll leave the check by you. This one here exactly matches this one here. Right, so we're done. So after fixing the 2 guards, now we got all the 4 sequence related to invariant preservation proved. All right. All right, any question here? All right. Just get the big picture clear. Don't get too much lost in the detail, and just make sure you can do the proof. All right. I'll move on. Let's now start with initializing the system, establishing the invariance. So if you go to slide number 30. Okay. And so let's see over here. So what we did earlier was about the 4 sequence related to invariant preservation. That's something we have done. But now it is important for you to know not only that you want to make sure invariants are preserved, are they established in the beginning to begin with? That's an important question to answer. So this is what we're going to do right now. And there's some analogy for you. I'm pretty sure you guys have seen a mathematical induction, right? So it's really about inductive cases that we have done so far to do with preserving the invariants. We also need to make sure the base cases are also satisfied, right? That's about establishing the invariants. Right, so just some visual over here just to show you. You can think about this will be the init events that we want to focus on right now. Think about induction. So base cases will be when we first when we first initialize all the variables of the system, we want to make sure this initial state is so-called safe, meaning that all the invariant conditions must be satisfied for the very first time after initialization. Okay? So this is very important. So this here is going to be green, meaning that it's safe. Establishing all the invariants for the first time. This is what we're going to focus on right now. But what we covered earlier is the more general case to say, if you have some pre-states and then some event occurs, you want to make sure the post-states also satisfy the invariance. That's about preservation. Okay? So assuming that this pre-state over here, pre-states assume to satisfy the invariance. And we talk about different events. For example, if we talk about ML out, also we got to talk about ML in, different events. And we want to argue that the post states over here show that it's provable that the post state also satisfy the invariance. Show that it is provable for the events to preserve the invariance. Right? This is important, okay? Visually speaking. And if you remember in the induction case, you basically say, assuming that P of n is true, we want to show that P of n plus 1 is true. Think this is more like a pre-state that we're talking about. This is more like a post-state that we're talking about. Right? Just an analogy. Okay? Pretty simple. Okay? And a little bit more to say about the initialization event. It's pretty straightforward, but there are certain rules you have to remember. Let's see the slides. Right? Individual cases are like the initialization. Think about P1, P2, P3, and etc. These are like individual initialization of the variables. Collectively, they are the base cases. And establishing the invariance, that's something we'll do. And then there's something we did earlier, which is about assuming that the pre-states satisfy the invariance. We want to show that the post-states also satisfy the invariance, preserving it. Okay? Okay, so now let's talk about this initialization events. Of course, this one here is pretty simple. We only got one variable, n. So we just assign that, or just let it become 0. Let's now go over some rules, just to make sure you understand them. Okay, so the interpretation is pretty easy. You want to make sure the number of cards in the island bridge compound is initially 0. That makes sense. Okay, and initialization is always possible. It's unguarded events. That's the only events you should really have no guards. All right, let me write it down. This is the only event that should be unguarded. The only events that should be unguarded. So what that means is initialization is always possible. Initialization is always possible. On the other hand, for any other non-init events, for example, ML out and ML in, if you don't see any guards for either one of them, that should be a problem, the opposite. So that's why we couldn't really discharge some of the preserving invariant proof obligation. So we had to add one guard to here and one guard to here, right? They have different constraints. Init should never have a guard, but all other events should always got some guard to make sure all the regular events are not always unguarded. Okay. And let's see the second one. And there's no pre-state for init. If you look at the diagram here, you can see I didn't really draw any circle for the init. So that means whenever you want to do inits, you basically do it, all you expect will be the post states. Okay? There's no pre-states. And this one is better to illustrate from the diagram. So there is no pre-states of the initialization, which means you don't really have to check any condition in the pre-state for init. There's simply no pre-states. It's always enabled. And the next one must not involve variables. So whenever you see the right-hand side over here for the inits, this must be either constants, just constant, always constant. On the other hand, if you say n is initialized to be n plus 1, this is wrong. Okay? This one here is not invalid init action. Not valid init action. Because there is no pre-state value of n. Some analogy I can think of, I'm not too sure if that makes sense to you. Let's say you're trying to initialize your system, and maybe the memory is already available there, but the initial value for all the variables might just be some junk. You don't want to really use it. So you want to just initialize all the variables with some meaningful values and use them from then on. But in the beginning, you just cannot use them. Okay? This is important. All right? This is a no-no for init. Okay? So far, still straightforward. Only involve constant, what I just said. There's only post state for the init. You can see that this is the post states for the init. That's the post states. Post states of init. All right, so that's what you need to know about the syntax for init. So whenever you want to declare your init events, just make sure on the right-hand side, you never put any variables. All right? Always constant. For example, what you did in lab number 1, you might say the B function is, becomes empty set. Empty set here is definitely not variable. Okay, it's a constant or some expression value. Any question here? All right, having known this, I think we should go ahead and talk about the proof obligation. All right, let's now talk about the proof obligation. And I'll just talk about it. So this part here is already covered on the page. Let's now get to it right away. All right, here. So this is what we have in the model so far. So we got our constant, and we got our axiom, we got our variable, and also we got our invariants. We don't need to show any events over here. They are not relevant. We're now only talking about invariant establishment. So we only need to talk about init. And this is n becomes 0. And what's the before-after predicate? That could be useful too for later. So if you look at the action over here, the before-after predicate is simply n prime equals 0. Right? That's also easy to see. And this is the proof obligation rule for invariant establishment. All right, let's now try to read it together. And this part here, if you recall from the component, this means all the axioms. We don't really have to involve any invariants. Invariants are usually to do with the variables. Since there's no pre-state for the initialization event, so we don't assume anything on the variables. All right, that's why. I can write it down for you. So this one here is axioms. And then you may also want to make a note over here. No invariance assume. Because they simply have not been established yet. Right? The very purpose about the init event is to establish the invariance. So that's why there's no invariant to assume to begin with. because not established yet. Not established yet. Okay? And then one thing to know here, also we learned from earlier, if you look at I, index I, this tells you that there might be multiple sequence you have to generate if you got multiple invariant condition. So the I here is the index of the invariance. Index of the invariance. In this case, we got 1 and 2. Okay, we're going to need 2 proof sequence later. And the invariance is going to be somehow expressed as the C, which will be the constants, and also KC. This will be the effects of the init action. There's something I will ask you to maybe look up by yourself. So the KC over here, by definition, is the effects of the init action. There's something else we learned earlier. I'll put it here, which is E, constant, and variable. Okay, in case you're wondering about what this is, I can tell you now, but you got to review. All right. This one here is the effects of regular events. Non-init event. Now, just from the math component, let's observe something very important. You can see the effects for any non-init events is going to depend on some constant, which is the same as the effects for the init. But there's something else that the effects of regular event depends on, which is the variable. You can see for the inits, we don't have variable, right? Because there's no pre-states. Okay, notice the difference here. Regular event can reference variables. On the other hand, if you look at just this part over here, init events can only reference constants. No V. Right? And the V here will be the before-after bracket. Okay, that's easy to see. Okay? Now, let's now get to the important part. Based on the model over here, and also based on the proof obligation, how can we generate the proof obligation sequence? Right? That's the next step. Okay? How many of them? 2. Because we got one invariant condition to be shown as established, and the second one to be shown as established. 2. Okay? So there'll be 2 of them. And let's look at their name, the naming convention. It's going to be very similar to the invariant preservation. You got to specify the name of the events, and also the condition, and also the nature of the proof obligation. So let's do one by one. So the name of the events will be init. And then we have, in condition number 1, invariant model 0, condition 1. And then we got the nature of the event is to do with invariance. In this case, establishment. That's one. Another one would be the init invariance 0, 2, right? This one here. And then INV. Number 1 and number 2. Each one of them should be a sequence. Both of them should share something in common in this part over here. Right? That one should be axiom. Let's do that. Let's do these 2 in parallel so you can really see how things should be worked. Turnstile, turnstile. And this part here is just axiom. Axiom, only one. So I'm going to put D is a member of natural number. And also D is a member of natural number. Assuming this, we want to show that after the execution of the events of init, the action should be able to establish the invariance. And I would suggest we do something very similar to what we did earlier. Number 1, you want to put the invariant condition first, intermediate step. So I will put invariant condition that will be n is a member of natural number. And the second one, n less than or equal to d. It's not a final answer just yet. Put it first. And then we want to transform this into the final answer. The way to do it is by considering the before-after predicate, which is over here. Okay? Oh, sorry. That's the invariant here and the invariant over here. We want to say that in the post states of, so after executing the init events, the post state over here should really satisfy that invariant for the very first time. So what we should do is first step is to copy it. Second step, we want to prime the variable. So make sure you prime that. So prime here and prime here. To say that the post state for n after the init event should be a member of natural number. And also the post state of n after the init action should be less than or equal to d. Almost done. And we know that the before-after predicate is n prime equals 0. That's something you want to do. So if you try to draw the connection here, so one will be from here to here. The other one will be from here to here. Okay, hopefully that's clear enough for you. All right, so the final answer would be n prime can just be substituted by 0. So I'm going to put 0 is a member of natural number. And also 0 less than or equal to d. So final answer would be something like this. This turnstile, this. This turnstile, this. And of course, you can see also the answer on the slides. All right, any question about this? Yes?
How come n prime is the post state instead of the pre-state?
Oh, this one here? Okay, think about this diagram here. If you think about the diagram here, let's start with this. Conceptually, if you have the execution or occurrence of the init events, it starts with nowhere. Think about. There's no pre-states. It's just the very first event to start with. And then after that, we want to make sure the invariant is established for the very first time. But as far as this init event is concerned, this state is its post states. That's why we got still add prime to the end. Yes? Sure. Because we know that as far as the init event is concerned, we want to make sure the states upon its termination, which is the post states, still satisfy the invariance. Well, satisfy the invariant for the very first time. So that's why we got to say prime. Let me say a little bit more here. The post states of events, so that one there will have the prime version of variables. So that's very important. So just remember, for regular events, you do have the pre-state, which is unprimed. But also you got post-state that's primed. But for the init, it's only the post-states that's primed. Okay, make sense? Good. Yeah, awesome. Yeah, think about it. You can definitely come back if you got trouble understanding it. But the way we actually copy the invariant condition first, and then prime the variables to represent the post-states, and then go to the corresponding before-after predicate, and do the substitution over here, just the same as we did earlier for invariant preservation. Just make sure you practice this. You might need something like that for written test number 2 later. Okay? You still have time to practice. All right, so the next step will be discharge these two. Luckily, they seem pretty straightforward. Usually, discharging the invariant establishment condition should be very straightforward, unless you do something very wrong. Okay. Let's see the slides over here. So we got 2. So these are the 2 that we just came up with. And let's now try to prove them. This is condition number 1. This is condition number 2. And again, I'm going to give you the hints as usual in the lecture to save time. Now, how do you complete the proof of this versus this? And these are the relevant these are the relevant inference rules for you. Take a look for 2 minutes or 1. And we're going to complete the proof. You want to think about these two. How are they going to be somehow transformed into some terminating inference rule, like an axiom rule? How do we do that? Both of them should be very straightforward. But it's good practice, right? You're still learning about this sequence style. Anybody want to volunteer? I can tell you the second one is easier. This one might be easier. Anyone? If no one volunteer, I will just tell you what the answer is. It's okay. All right, let's try. Of course, in the actual test, it will be more challenging for you because you may not be given only these 3 rules for you to consider. So you really want to make sure you can practice this, right? Okay, I can tell you that somehow I can use this, I can prove this by P3. How come? If you see the pattern here, 0 less than or equal to D, 0 less than or equal to N. And then D, natural number, N, natural number. So we're basically instantiating the P3 over here by replacing N into D. That's what we're doing. All right? Maybe try to make sure you're convinced about the pattern here. All right? So P3 tells us in order to prove this sequence over here, nothing else to prove. It's an axiom. Okay? Good. And for this one here, you don't need to say anything else. You can just say it's proved by P3. And it will be very nice if you can also say where the N here is instantiated by the D here. Usually, it might be not so obvious for you to really say this will be the terminating sequence. You really have to see the pattern in the axiom inference rule. All right? That's the key. All right, how about number 1? Number 1 is slightly more complicated, but it's not too bad. Let me ask you this. Can I say this one here, and then say that it's proved by P1? Number 1, can I or can I not? Oh, good. You say I cannot. Can I trouble you? You say I cannot. Tell me why. Why not?
Because you can just apply 1 first to get the empty and true, to extract the true from the, how do you call it?
To get rid of the irrelevant hypothesis.
Yeah.
Okay, that's very good. Okay, very nice. So your classmate was exactly right. So over here, I cannot, okay, let me write it down as well. If you here, you simply say this is proved directly by P1. This is wrong. Because if you look at the pattern here, this part here, I agree, matches this part over here. However, if you look at to the left of the turnstile, it's empty. But now, above the turnstile, it has something here. So they don't really exactly match. So you cannot apply that just yet. But you can easily set it up so that you can apply. So you want to get rid of this irrelevant sequence. I don't really need it. Just drop it. Okay? So just saying that it's P1 directly is not going to prove it. Instead, we're going to do as follows. By monotonicity, I can transform that into this sequence over here. So I drop this one here, and then turnstile 0 is a member of natural number. And this one here matches P1 pretty well. So P1. So that'd be the correct proof. right? Easy proofs. But it's also worth practicing, especially when you're only beginning to learn about sequence style proof. All right, any question? All right, if no, so we can now move on a bit. All right, the last bit that we need to speak about, M0, is deadlock freedom. This is a very important topic over here. All right, so before we show you the slides, let me give you a little bit idea about what can be expected for deadlock freedom. Because now we don't really have any refinement just yet. We only talk about a very initial model. In this initial model, we can already talk about deadlock freedom. But later on, when we introduce the first and second refinements, we have to somehow say the refinement can preserve the deadlock freedom. That's something we'll do later. I'll just give you some look ahead. All right, so for bridge controller, we know that we are talking about, oh, sorry, forgot to switch. There we go. Let's make some sketch. For our bridge controller, it is a reactive system. Bridge controller, we know that it's an example of reactive system. Reactive system tell you that it should always work. There should be always at least one event that should be available to occur. There is always at least one. At least one event enabled for the system to progress. This is a very important conceptual idea for you to remember. Okay? So what would be unacceptable? Based on this, we can now define what is unacceptable for reactive system. What's really unacceptable for reactive system would be if we run into deadlock. And deadlock definition is simple. Deadlock simply means no events enabled. Enabled to occur. So your system basically gets stuck. No way to make any progress. Okay? And now we want to somehow, based on this, we want to actually sketch out the mathematical condition for that. All right? And let's assume the following. Let's use some notation here. Let's say we got two things. For our bridge controller so far, we got two events, right? We got ML out, and also we got ML in. Right? These are the two events. Let's say we have some function g to retrieve the guard. So this expression over here is going to give you the guard for events ML out. This is going to give you the guard for events ML in. What they are exactly, we'll get to it. But for now, just conceptually, right? We got two guards. And of course, if you got a model with more events, you just got to put more guards into the context. Okay, for now, just two. Now, I want you guys to think about, and once you get this through, the proof obligation itself will be much easier. Now, here's my question for you. How do I formally express the deadlock condition? If I say deadlock happened, then that means no events is enabled. That means this is not enabled, and also this is not enabled. How do I express this deadlock condition logically, using logical operators? This is an important step, because once we understand how to formulate the deadlock condition, we can take the negation of that to express the deadlock freedom condition. And then we can get to the proof obligation. Right? Again, I'm just preparing you for that. Anyone? How do I express the deadlock condition? Under what circumstances, in terms of the guards for ML out and ML in, we're going to get into a deadlock situation where no event is enabled?
The guard is always false.
The guard is always false. You mean for both of them? How would you, I agree, informally. But how do I express that logically? Let's say, oh, apparently this is a Boolean condition, right? This is also a Boolean condition. How do you somehow combine them together into a single Boolean condition that's going to represent deadlock situation? Okay, so I like that. But if you say and here, that means the guard of ML out is true, and also the guard for ML in is true. It's not exactly deadlock. Deadlock should be both of them being false, right? Okay. This is a deadlock condition, right? Are we okay so far? Okay, this is called deadlock condition. And let's play with that a little bit. Let's use De Morgan. All right? Would you agree? This condition here for deadlock is equivalent to not the case. What should I put inside? Or, good. You guys are good. Okay, this one here, or this one here. All right, we're getting there. I think just easier for you to understand this kind of flow. So this will be ML out and also ML in. So this is also equivalent deadlock condition. And now I want to take the logical negation of this, which I just take out the negation sign. So the final condition I would need for this page is this condition here. So finally, I got something like the G of this or the G of that. ML out, ML in. That's what I have. So this is so-called the deadlock freedom condition, which is the negation of deadlock condition. Deadlock freedom condition. Okay? So this is to say, whenever you talk about a system, for example, a reactive system, where deadlock freedom is really important, how do you formulate it? It would be either the guard of one event is true or the other guard is true. It will be deadlock if none of them is actually true. Right? So this will be the deadlock condition. So think about this one here versus this one here. Both of them has its value for interpreting. All right. If no further question, let's now see the actual proof obligation rule. And it'll be very smooth once you understand how this actually is derived. All right, so the proof obligation here goes like this. We got a sequence over here. So DLF stands for deadlock freedom. Deadlock freedom. All right. And then let's look at the above and below the turnstile. And this part over here, you can see that's an axiom. And this part over here is the invariance. And now this part here should not appear very weird to you. What does that mean? All right? This one is to say, Assuming that you got event 1, you got event number 1, event number 2, all the way to event n. You got m events. And then, okay, let me use this one here. So how do we interpret this? At least one of the m events is enabled. That's how you interpret that. If you got 2 events, you just put 2 event guard into disjunction. If you got m events, just put them, the guards together in disjunction. All right? That's the formulation. All right, guys, any question about the proof obligation rule? We're okay, right? Okay. Now, how do we write it down? Okay. For our model here, let's now do one by one. We got axiom, which will be this guy here. It will be D is a member of natural number. And also we got invariants. We got all of them. This one here. Okay, we got N is a natural number, and also n less than or equal to d. All right? And then we got turnstile. And what about this part here? Right? It's going to be the disjunction of all the event guards. One event guard over here. This is the second event guard. So here for the MLL, MLN, I'm assuming that I have already fixed the model based on the invariant preservation feedback, right? Now, all I got to do is I can now put n less than d or n larger than 0. And this one here, oh, let me use a different color. This one over here is the guard of ML out. And this one here is the guard of ML in. And one thing to note, actually, right? You can see the way we figure out the de la freedom proof obligation, especially the goal that we want to prove. We didn't involve any post states, unlike before, if you recall. In the case of the invariant establishment, you remember we had to somehow copy the invariants and make the prime version, because the invariant must be established in the post states. Also similarly, if you go back to the earlier notes, where we do the invariant preservation sequence, and we also need to copy the invariant over here in the go and prime the variable to say the invariant must be preserved in the post states as well. That's something you can look up as well. But in the case of de la freedom, we didn't do anything like that. It is because whenever you talk about de la freedom, it's really about whether or not the events are enabled in the pre-states. There's no post-state idea over here. Okay? That's something you want to know as well. I'm going to write some table to compare. But for now, you just got to also remember de la freedom is really about event enableness in the pre-states. Okay, that's important. Okay, in the pre-state only. All right, any question? Let's now conclude by making some table. Okay. So I'm going to put it here. So let's have a table here. So far we talk about 3 kinds of proof obligation. We talk about invariance establishment. And we talk about invariant preservation. And we talk about deadlock freedom. And we want to know what states does each one of them involve. Do they involve pre-state, post-state, or both? Okay, that's a good summary for you. All right, so we talk about the pre-states. In this case, for example, you just have n. And also you got the post-states, in which case it's going to involve n prime. right? Of course, in general, just be V and V prime. But for this example here, just do N. All right, let's now see what should be applicable, right? That's a nice check for you. The one we just did about de la freedom. It definitely only involves the pre-states, but it does not involve the post-states. It's only about enableness of the events. What about invariant establishment that we just talked about today? Does it involve the post-states? That one for sure, right? If you look at the diagram here, if you don't mind, let me go back quickly. It only involves the post-states, but there's no pre-state, okay? So that's why it's going to be something like this. So the post-states, yes. But for the pre-states, no. Oh, wrong place, beg your pardon. The post-states, yes. But for the pre-states, no. How about finally, what of invariant preservation? What are pre and post states? Both? Yeah, I agree. Yeah. Because in the invariant preservation, if you look at the diagram again, that will be an inductive case for us. So you can see that given some pre-states where invariant is assumed to be true, we want to show that it's maintainable, right? Okay, so both of them are involved. So it's going to be this and this. Question? Why does it? Okay, the reason that de la freedom involves the pre-state conceptually is because de la freedom has to do with if all the events are not disabled. Put it in this way. If you go back to this sketch over here, it would be de la free for the system if either this event is enabled or this event is enabled. If none of them is enabled, you'll be deadlock. Okay, now, why does it involve the pre-state only? The way for you, the way for you to judge whether an event should really occur is whether or not in the pre-state over here, the event guard is enabled. If it is enabled, then event will occur. If the pre-state doesn't really satisfy the guard for the event, then it's not going to occur. Okay, that's why. So de la freedom concerns nothing about the post-states, just the pre-states. That's the important message for you. All right, let me do one more thing, and then we'll take a short break. One more thing, okay? And once we got this guy here formulated, we need to prove it. So we're going to do that after the break very briefly, and then we're done. But before that, before the break, let me show you guys some new inference rule, okay? New set. Here, all right? Again, this, and this, these are the axiom inference rule. You can see the above, they're empty, all right? This one here is so-called a hypothesis rule. If the hypothesis happen to be the goal, then proved. Because you assume P, of course P is true, all right? So if the goal matches one of the hypotheses, then it's automatically proved. And this one here is false L. And the way to understand it, which I explained earlier, but let's brush up the mind. The L here simply means if the false occurs to the left of the turnstile. You can see the turnstile is over here. To its left, you got something called false. Okay, so this is the false. So this is true, and the bottom here is the false. I believe in 1090, if you ever saw these symbols, this is called top, this is called bottom, right? Okay. So if the false appears to the left of the turnstile, it will be as if you say false implies P. Of course, it's automatically proved, right? Don't forget the turnstile also means imprecation, formally. So this one will be corresponding to the false implies P, right? Which is equivalent to true. And this one, something similar, if the true appears to the right of the turnstile, that should be automatically proved too, right? So this one here, you can see the true over here appears to the right of the turnstile. It would be as if we say P implies true. That's equivalent to just true. Right? That's also proof automatically. And if you got on the right-hand side, the goal, if you got something equal to itself, it's also automatically proved. Doesn't matter what the hypothesis is. So it's called equal inference rule. All right? That one is also straightforward. Now, I got to clarify about these two. So these two have to do with equality. So if you look at these two rules, you got E equals F over here. E equals F over here. Right? In both cases. And in this case, to the left-hand side of the equality, we'll call it the left. So think about this one here is the left. So this guy here is the left. And this guy over here is the right. And this one here is a right. Okay? And this is to say, if you already got some hypothesis that's defined, let's talk about this one here first. Okay? Let's talk about this one first. EQLR. I got equality, and I want to go from left to right. What does it really mean? It means the following. If I got some hypothesis, and also I got some goal over here, both of them are defined in terms of the left. You can see here, I say I got some hypothesis, I got some property goal, and both of them are defined in terms of the left. Symmetrically, over here, I'm saying that I got some hypothesis, H, and I got some hypothesis, some goal, P. Both of them are defined in terms of the right-hand side. You can see F here correspond to the R, right? Okay. Now, what will be sufficient to prove in each case? If I got this, where the hypothesis and the goal are defined in terms of the left, it would be sufficient to prove by substituting every occurrence of E over here and here by F. So that's why it's so-called from left to right. Okay? So go from E to F. E to F. Okay? The rule itself is very abstract, I agree, but you got to know there's such a rule. And then once we get to the special occasion to apply them, it's very straightforward. So the way to understand this LR would be replace every free occurrence of E by F. Right? So replacing E by F, we say it's LR. Replacing F by E, we say it's RL. Right? Just remember the order really is important. All right, I think that's enough for you to really study this rule a little bit further yourself, but you get the idea. Any question about this? All right, if no, why don't we pause for a minute and take attendance and take a short break, and then we'll resume. Okay? All right, so for M0, we just got two more things to be done. Number one, we need to try to prove the de la freedom proof obligation, which we formulated before the break. So this is, oh, sorry, not this way. So this is something that we formulated before the break over here. Okay, that's what we did before the break. And let's outline them more nicely here. This is the one. This is the de la freedom that we want to prove, discharge. This is the de la freedom proof obligation before the break. Okay, and this is something that we really tried last time. Okay, so I'm not going to repeat the efforts again, so we can save some time, but let me tell you the highlights over here. Okay, so when you try to practice this particular one, again, I gave you all the hints about what's the relevant inference rule that you're going to need, right? So these are the relevant ones, including the ones that we learned earlier and also the one we just learned before the break. And starting with this, by some arithmetic, basic arithmetic, we can split this into n less than d or n equals d. That's something we did something we did last Thursday. This is nothing new. And then we can split the sequence into these two. Okay? For this very initial proof, that's something I will let you actually try to. That's the only thing I want to show to you is this. Let's say we got into here. And then we're going to use ORL. The way to use it is like this. N less than d is one of the disjunction in the hypothesis. N less than d, n less than d, let me draw better. There we go. This one corresponds to this one. And also this one here corresponds to this one over here. Right? And you can see the goal over here remain the same. Right? So I'm really applying ORL. And if you proceed with this particular branch, you can see I can choose ORR1 to say I just want to prove this one here. Right? So that's why it's here. So this one over here is now selected. And that one there corresponding to this one over here. And you can see the goal matches one of the hypotheses. So by hypothesis axiom rule, this branch is proved. But we still have to complete this guy over here. All right? So now let's see how we can proceed with this. Whenever you see this any hypothesis part that has some equality, you may want to consider using E cube, either LR or RL. All right? That's something we spoke about before the break. And in this case, I would suggest you try EQLR. Sorry, I don't have it here, but I'm going to copy that right away. So EQLR. Oh, sorry about that. Let me copy it again. Let me try to get it back. How can I just get rid of it? There we go. Okay, let me copy again. We're going to need EQLR. So let me copy that. That's good. And put it here. There we go. Okay, let's now review what EQLR is supposed to mean. If I try to apply EQLR on this one here, right, you can see N equals D correspond to E equals F. All right, you got to identify which one is the left, which one is the right. N here is the E. D here is the F. All right? Let me write a little bit better. N is here, and D is over here. And what's really, there's no more hypothesis. You can think about HE is empty. But what about this guy over here? That's a P of E. That one here is really the expression over here. The P of E is basically N less than D or N larger than 0. EQLR. That is to say, I want to replace every occurrence of E by D. Right? That's how I interpret the rule. So now where is E? This one here, and also this one over here. Replace every occurrence of them by F, which is D. This by D, this by D. All right, that's something you want to also practice yourself and convince yourself. It's really applying the rule. Okay, once I've done that, I'm going to get D less than D, and also D larger than 0. And usually, when you do EQLR, once you have done the replacement, this equality here normally can just be dropped. It's not relevant anymore. It may not be so useful anymore since I have done the replacement. So when I say EQLR and also monotonicity, I basically drop this one at the same time. So that's why it's not here anymore. Okay? And then I got this guy over here to be discharged. So I got either this or this. And finally, it turns out this guy here is false. If you think about this guy here, D less than D by arithmetic, I know that it's really false. So it doesn't really make sense to really choose this one to prove. So what we should really choose instead will be the right-hand side. So there is an alternative over here, which I can show to you very briefly. So this one, alternatively, you can say, I got this one here, D less than D, or D larger than 0, right? You can say by basic arithmetic, this one will be false, or D larger than 0. And by another arithmetic, right? So here I can put some explanation to say D less than D is equivalent to false. And then this is another arithmetic. I can say false or any P will just be equivalent to P. So now it'll be very obvious, right? So I can now get rid of this one here. I only got the right-hand side left. Effectively the same. After this, it's going to be just D larger than 0. So from here, you can either go for this root over here, and it can end up being here. Or you can simply go for ORR2, which will end up being here. Either way, both work. But now we have some problem. The initial proof about de la freedom will leave us to D larger than 0. This turns out to be unprovable, because I simply have no other hypothesis to really support this. Right? So this is unprovable. Unprovable given no additional hypothesis. You can see a hypothesis over here is simply just empty, right? Nothing for me to use. So this is something that we have to work with. So don't lose the big picture. The big picture goes like this. We try to formulate the de la freedom proof obligation here. That's what we did before the break. And then we try to prove it. And once we get to prove it somewhere, we actually split the sequence into two. We are able to prove one of the branches. But for the other one here, we end up being D larger than 0 being the goal, then we cannot go any further. So there is something wrong with the model to prove about de la freedom. Are we okay? Okay. I would suggest that we only got about 5 minutes. Before Thursday, make sure you review everything up to here for the bridge controller, especially how we really try to tackle this particular proof. You really want to make sure you follow that, right? Because once we get to M1, M2, we may not do that many proofs in class. I may just need to assign them to you for exercises, okay? And before, to start the Thursday lecture, we're going to interpret this and fix the model. And then we are done with M0. And we're going to move on to M1. All right, okay. Thank you. I'll see you tomorrow in the test.